All right, let's take a look at the practice test together. When you first look at this table in number 1, you might say to yourself, what the heck is going on? But don't give up before you start. So what this is saying is you've got this fake element benium, okay? And they're representing 3 different isotopes of benium with kidney beans, pinto beans, and black beans. Your job is to calculate the average atomic mass of benium. So what we're going to need to know is the average mass of each isotope and their relative abundances. Once we have those circled spots, then it's easy. Then it's just plugging into our formula. So let's take a closer look at what's going on here. So they've got 45 kidney beans that all together weigh 9.5 grams. So how do you figure out how much each kidney bean weighs? It even tells you here, take the total mass divided by the number of each isotope. So we do 9.5 divided by 45. That means each kidney bean weighs 0.21 grams. Okay, we already know pinto beans' mass of each, and this is really not even information we need, but just to prove we understand this table, how much would all 13 pinto beans weigh together if each one weighs 0.15? So you have to multiply these two numbers, 1.95 grams. Finally, there's 120 black beans. All together they weigh 12 grams. So how much does each one weigh? I do 120 divided by, 12.0 divided by 120, and that's 0.10 grams. Now we're missing a percent here. 25.3% of all of the beans are kidney beans, 7.3% are pinto beans. So what does that leave here? Let's just do a subtraction from 100%. So 100% minus 25.3 minus 7.3 comes out to be 67.4%. And then to get the relative abundance, just move the decimal 2 back, so 0.674. Now we're ready to plug and chug. So we're going to take the average atomic mass of kidney beans times how often they occur, 0.253, plus the average mass of a pinto bean times how often they occur, plus the average mass of a black bean times how often they occur, and voila, we get 0.13 grams as the average atomic mass. Now let's see if this makes sense. Most of the time, 67% of the time, they weigh 0.10. So this is pretty close to that. These that occur but aren't as frequent are heavier, so those are driving that average up. Then we've got a little table to complete. What would the name of this be? Remember, for isotope names, you name them after their mass. So this would be aluminum-29. That mass number is in the upper left corner, 29. 13 protons, 13 electrons. Those match in a neutral atom. And then neutrons, we got to do a subtraction. 29 minus the 13 protons equals 16 neutrons. Okay, then we've got some information about element number 33. Well, that is arsenic, if you look it up. How many electrons would it have if it's neutral? 33 protons, 33 electrons. 33 protons. Neutrons in the most common isotope. Well, you have to look up the average atomic mass of arsenic. And on the periodic table, it rounds to 75. So 75 minus 33 gives us the number of neutrons in the most common type of arsenic. Number 4, choose one of the models of the atom that we've talked about and describe it in detail. Why did the models change over time? Will it change in the future? Just as a little recap, they used to think that atoms were just shrunken down billiard balls. They called it the billiard ball model. They said there's no charges. They're just small, dense pieces of matter. Okay? Then, with new technology, they used something called a cathode ray tube and made the plum pudding model because they found that every single element has a negative, something negatively charged in it. So they said, okay, it's like plum pudding. The raisins are the negative charge, and the pudding is the positive stuff. Okay? Then they did the gold foil experiment. Remember, they shot alpha particles at a piece of gold foil, and most of the time, the particles went straight through to the other side. But 1 out of 8,000 times, the particle would bounce straight back, which was crazy to them. But they figured, okay, this means that atoms have a small, dense nucleus in their center. It also meant that atoms are mostly empty space. Then they did some more experiments, and they figured out that electrons are actually in specific distances away from the nucleus. And finally, they said, okay, you know what? We can't say that we know that there's an exact electron in any spot at any time. So they've got protons and neutrons in the nucleus. So some things that are positive, some things that are neutral. And then they draw the electrons as a cloud of where it probably is, but it's impossible to know the exact location. Will this model change in the future? You bet. Number 5 says, draw a picture of element number 19, include protons, neutrons, electrons, be specific about where they are. So protons and neutrons are in the nucleus. Potassium is number 19, so 19 protons. And if I look at its square, it says the average atomic mass is 39.0 something. That rounds to 39. 39 minus 19 is 20 neutrons in the nucleus. Now the electrons are all around. There are 19 electrons in the cloud. What accounts for the size of the atom? The electron cloud, where the mass of the atom comes from the nucleus mostly. Electrons still have mass, but they're so tiny. All right, good luck.